Hello, pre-calculus class, and welcome to your first lesson in quarantine. For every future class that I use this for, welcome to the lesson that was the pre-calculus class of 2020's first lesson in quarantine during the coronavirus pandemic. We are going to be learning how to optimize today. We're going to continue what we were doing in our last lesson in section 12-3 in that pre-calculus book. Just trying to figure out, how do we optimize anything? How do we make something be the biggest and best that it can possibly be? In this case, we are going to be trying to find the maximum volume of a cone inscribed inside of an ellipsoid. So the problem written up here says we have an ellipse given by this equation, this 25x squared plus 9y squared equals 225, rotate it around the y-axis. So kind of think about, right, we have this ellipse that we're going to draw. We're going to rotate it around the y-axis to form an ellipsoid. The cone with its vertex at the origin has its base inscribed inside the top half of the ellipsoid, and we're trying to find the biggest one by volume and find the radius and height that gives this thing. So the first thing that we have to do, right, the first thing that we have to do is visualize what's going on here. So we have to sketch the situation here, right? Sketch what this would look like. So we want to graph this ellipse. We want to rotate it, right, to get the 3D effect, and then sketch the cone on the inside there. So first we have this equation. We have this 25x squared plus 9y squared equals 225. That's an equation of an ellipse, but it's not a particularly useful one. So what we want to do is figure out, right, we want to find the center radius form of this ellipse. So that we can actually graph it, right? Right now I don't know what the x radius is, I don't know what the y radius is, I don't know if it's longer than it is. So we want to take that equation, that 25x squared plus 9y squared equals 225, and we want to write it in that form, that like x divided by the x radius squared plus y divided by the y radius squared equals 1 form that we were used to seeing at the start of this section. If you're not fully comfortable with that, go back to the last set of notes, the 12-3 notes. There are some notes in there about rewriting that. But we want to take this and get it into this form here. So first thing I want to do is I want to set the right-hand side equal to 1. Right now I have 225 there, so let's go in and divide everything by 225. Divide all of the terms by 225. That creates 1 on the right-hand side here. And then 25 over 225 ends up being 1/9. Right, so I get x squared over 9. And y over 9 over 225 is 1/25. So I get y squared over 25. So 9 225ths is 1/25. 25 225ths is 1/9. And so I get this simplified thing. Looks pretty similar now to this up here, again, this center radius form that I want, but I don't have the x radius and y radius inside the parentheses, so I have to think of like what would those be. This would become, right, like I could write it as x squared over 3 squared and y squared over 5 squared equals 1. And then I can put those, right, the x over 3 inside of parentheses and square it. I have y over 5 inside the parentheses and square it, and that would be equal to 1 there. So now I have it in this center radius form. I have my x radius, there's 3, I have my y radius, that's 5, and I can sketch this, right? So give a little grid. I'm really only looking at the top half of the ellipsoid coming back up here. So I'm only going to sketch half of it. I don't need really the bottom half. The cone is only in the top half. But I'll have this sketched down there. We'll space this out, like there's my x, there's 1, 2, 3, there's my x radius. And going backwards, 1, 2, 3, where it's going to come back and hit. Scale this the same. 1, 2, 3, 4, 5 is my y radius. So I have this ellipse. X radius of 3, y radius of 5. The whole ellipse would end up going back underneath, like I would have this like finishing off down there, but I don't care about that right now, so I'm just going to draw the top half. Okay. So I have that ellipse. We want to rotate it then around the y-axis, is what it says. So I'm going to take this and think about, like, if I took this and spun it, right, like this would kind of go into the page around there, and then come back out of the page. I get this ellipsoid, right? It would be a prolate spheroid, that pill kind of looking thing. So there's my ellipsoid. The last thing we need to do is think about that cone, right? So there's a cone that's inscribed inside of this ellipsoid. It says it has its vertex is at the origin and has the base of the cone is inscribed inside the top half of the ellipsoid. So my vertex is right there. And then somewhere in this top half, like the base of the cone, the circular base of the cone is inscribed in here. So I have this, right, kind of coming in here. And it would just fit on the inside of that pill type thing, right? And the rest of the cone would go down to there, right? So I've got my cone, I've got my ellipsoid. This is what this thing would look like, right? It has some radius, right? The cone has a radius that's there, and it has a height that's, right, it's this tall, whatever that is out to there. Right? So we are trying to find what is the biggest one, because again, this thing is dynamic. This thing can change, right? So I put in over here just a little, see if I kind of hit it intentionally at first. I'll bring this kind of over here to give you a little dynamic illustration of what this would look like, right? So here, like this is the same situation. We have an ellipse with a y radius of 5 and x radius of 3 out here. And then we have this cone that's inscribed inside of this, right? But that, right, we can sketch it in one location like I kind of did up here. We have that one radius, one x, y, like sample point that's sitting there. But it can change, right? Like that's not the only place that I could put that, right? That could be, right, the x and y coordinate could be a lot higher, and we'd get this really like tall, skinny cone that probably doesn't have a lot of volume. As I bring that out wider, right, and wider, I get this larger cone, right, that again gets wider, but it gets shorter, right, until eventually, if I take it all the way out, I have no height whatsoever. Right? So somewhere in here is the biggest one, somewhere between this really skinny, right, maybe even all the way up, right, there's no radius there, it's all just height, and this one down there that has all radius and no height, somewhere in between there is my biggest one that has the largest volume. So we are trying to find that. Right. I'm going to hide this again back kind of off over here. I'll leave it there for us, but right. So what we want to do, right, this is kind of your second step, right? A is first sketch the situation. B is I want to write the volume of this cone, right? What's the equation for the volume of the cone? Right. Well, the volume of a cone, and you'll be given all of these, is 1/3 pi r squared h. Right. But I know what my radius and my height are in terms of this x and y here. So I want to write the volume of the cone, not just that, but in terms of x and y. So it's not radius and height so much as like x and y coordinates. That's what I've been given in here, and what eventually I want to like relate these things to, right? Because my radius and height aren't random; they can't be anything. They're tied together, right, on the inside of this ellipse equation, right? As my radius gets bigger, my height has to get smaller, right? The height is related to that radius. They're not just kind of random things; they're put together. Right? So in terms of x and y, I know what my radius is, right? And this is always a huge step, right, that people tend to miss because they try to oversimplify it. In this case, it ends up being pretty simple. The radius of this cone it goes in the x direction, but beyond that, it is equal to whatever that x coordinate is, right? Whatever this x coordinate is out here, that's what this radius is here. So my radius of the cone is just x, and the height of the cone is the y coordinate in this case, right? It's y up here. It's going from 0 to y, so the height of this cone is equal to y. It's not always going to be that case, right? If this were, say, like a cylinder inscribed with the full ellipsoid, not just like the top half, right? If that came all the way down here, I would need to maybe make my height be twice the y coordinate, right? It changes depending on what the situation is. So when I give the solutions for the problems in the book, I'll make sure that I kind of highlight that. But always, right, this is a very key step. It's not always just going to be x and y. It might be like 2y, it might be 2x. So explicitly lay that out. But now that I have that, I can put those in, right? I know my radius is x, my height is y. So let's write the volume then. I'm going to substitute in x for r. So it's a 1/3 pi x squared, and my height is y. Right. So there's my intermediate step here. This still doesn't really let me solve for that maximum thing because I have my x and y are two separate variables, but I know that they are tied together through that ellipse equation. So my last step, the third thing I need to do is write the volume as a function of only one variable. And we usually make this be x, just because it makes the most sense when you're graphing this at the end. Right? Sometimes the math actually ends up being easier to make it be y, but the Desmos graphs look a little wonky. So I would usually say like choose it to be your x variable. Right? And so we know that x and y, right, they're not just random things. They are related through the ellipse equation. Right? As x gets wider on the ellipse, y has to get smaller. Right? So I have this equation. Let's go back to the original. We got the 25x squared plus 9y squared equals 225. What we want to do here is get the y by itself. Right? Ultimately, we're trying to get the y by itself, like write it as an equation in terms of y so that I can plug it in up here in this volume equation. I can substitute in, I'll have y equals some function of x, and I can put that in there so I can make my volume be only a function of x. So let's see what that looks like. Right? In order to get y by itself, I need to move everything away from the y. So again, reverse order of operations, kind of undo PEMDAS. I'm going to move that 25x squared first. So I end up with 9y squared equals 225 minus 25x squared. I'll divide everything by 9. Next, so I get y squared equals, I got 25 divided by 9 is 25. And 25x squared over 9, that really can't simplify, so I'll write it just as 25x squared divided by 9. Last thing I need to do, square root everything. So y is the square root of 25 minus 25x squared over 9. Okay. I have my y now as a function of x. So what I need to do is plug this in for y in the volume equation. Okay, that volume equation from up here. So I'm going to just take that, rewrite it over here. I've got my volume was 1/3 pi x squared y. And I'm going to take this, y is equal to that. I'm just going to do a quick substitution. Plug that in for y there. So we'll get my volume is 1/3 times pi times x squared times the square root of 25 minus 25x squared over 9. So now I have my volume as a function of x squared, or really as a function of x, right? That I can graph this in Desmos and figure out, right, where the maximum is. In calculus, you'll do this all by hand. Right? You'll take this equation and you'll figure out, like, hey, I can do that by hand to figure out, like, where the slope ends up being 0. For now, pre-calculus, we're just going to graph this and figure out, like, where is the biggest volume. So I'm going to graph this volume in Desmos. And find the maximum. Okay. So again, I've already done that. So I'll take this, hide that off to the side for now. And I have a separate second Desmos thing. Let's see, can I move it? I might need to get this one more out of the way. This one. This is my second one. Sorry about that. Right. So here's that equation again, just rewritten. I'll slide this over so we can see the whole thing. Right. My volume as a function of only x is 1/3 pi x squared times the square root of 25 minus 25x squared over 9. Ends up looking like this. And again, I know that when my x value is 0, the radius of this cylinder, or the cone, sorry, is 0, and it has no volume. Right? When the x value is 3, that means the radius of the cone is 3, but when the radius of the cone is 3, that means that I have no height. Right? So again, over here, just kind of looking at, right, if I take this up to the top, if my x is 0, radius is 0, I have no volume. Right? If my x is as big as I can go, all the way up to 3, I have no height, I have no volume. So that's what this is showing here. Right? These points are saying that when x is 0, I have no volume. When x is 3, I have no volume. Everywhere in between here, I have some positive volume. And this point right up there, that 2.449 and 18.138, that's the biggest volume that I can possibly get. Right? So that 2.449 here, okay, that is the x-coordinate on the ellipse that gives me the biggest volume. Right. And the 18.138 here, right, that is not the height of the cone, right? That's not the y-coordinate on this ellipse, right? We're graphing this as a function, right? It's my outputs here, the numbers that are outputting are volumes, right? The cone can't get higher than 5, right? So this 18.138, it's not the y-coordinate on the ellipse up here. It's the number that represents the volume, the output of this function, the maximal volume of this cone. So what we were ultimately asked to do, right at the very top of the prompt, we wanted to find the maximum volume of the cone. We found that. We wanted to find the radius and the height of this maximal cone. So we have the x-coordinate on the ellipse that gives that volume. We have the volume, but now, right, our very, very last step, we want to describe this maximal cone. So I know my volume. That's the 18.138. Let's put some units on it. It would be units cubed. The radius of this thing is the x-coordinate, right, which is 2.449 units. The last thing we were asked to find is the height. Right? The height is nowhere on here, but I have the equation for it. Right? Again, my height equation, the height is equal to y. Right? And the y was equal to the square root of 25 minus 25x squared. Right? But my x, I know, it's 2.449 squared, all divided by 9. Right? Plug that into your calculator. I get that it's 2.89 units tall. So I have there. It's the biggest one you could possibly go. If I went back up here, right, I can make my x value. I said it was 2.449. Oh, I think I could change it. Yeah, maybe not. Okay, I'll leave that alone. I can drag it still. Right, at 2.45. Right, that's the biggest cone that I could possibly make. So that is, generally speaking, how you optimize some things. So look for an assignment that's coming out, and I will probably record the solutions to that as well. Go a little quicker than this one, but so yeah, good luck.